This next part is likely to be a new concept if you are brand new to chemistry or really, high school, higher level science in general. This is making measurements with significant figures, which is something we must consider whenever we are making our own measurements in the lab. We also have to consider it whenever we are provided with values in solving problems that we may face in the future in chemistry concepts. Either way, we're going to say this frequently during this portion of the video. We are only as accurate as our least accurate instrument. Okay? Let's say that you are building a birdhouse, a really fancy birdhouse. Okay? You want a bougie house for your cardinals and the blue jays that are sitting in the backyard, making beautiful nests within to raise their young, lovely birdlets inside. Okay? And you've got two men on the job. Okay? And one guy uses this top ruler and one guy uses this bottom ruler. Who is more accurate? Well, it's a simple answer. The guy who's got more lines is going to be more accurate with his measurements. However, if one guy is responsible for measuring half and the other guy is responsible for measuring the other half, we are only as accurate as our least accurate instrument, in which case this is this ruler. And so we have to adjust our measurements and our calculations to compensate for our least accurate tool. So, specifically, the definition for what we were going to utilize here for sig figs is what we abbreviate significant figures. It includes all of the digits that you know plus one estimated digit. If you are making measurements in the lab and you don't have an electronic balance doing it for you, you have to estimate, which is really counterintuitive to a lot of us. Okay? I'm using a tool that is designed to measure, and I have to estimate. It's weird, but we have to get used to it. So what do we know about this paperclip? It's the same length on both of these pictures. However, one tool, one instrument gives us a little more information than the other. Well, on the top ruler, we know for a fact that this paperclip is at least 2 centimeters and it is less than 3 centimeters. We know that for a fact. We are accurate to the ones place here. So we have to estimate one digit past that, which means we have to go to the tenths place. Okay? And this is where there's a margin for error here. Of course there is. And so I would say, if it were me, I would say that's about 2.3 centimeters. That's me estimating that 0.3. If you said 2.9, you're wrong. We know 0.9 is way over here, but there is still a margin of error. If someone said 2.2, 2.3, 2.4, sure, all of those I would agree with. It's definitely not 2.5, right? We're not at the halfway point, okay? But it's in the ballpark. So there we go. We estimated one digit further. But what do we know about the paperclip in this picture? Well, it's definitely between 2 and 3, but we could go past that. It's between 2.3 and 2.4, if you can see that. So we know that the first two digits are 2.3. And we have to estimate it past it. If this is accurate to the tenths place, then we have to measure to the hundredths place. And if you're looking at this picture, it looks like it's just past that 0.3 mark. So I would say 2.31, 2.32, somewhere in that ballpark. I wouldn't say 2.39. It's not right up against that 2.4 mark, right? It's definitely closer to 2.3. But either way, I'm estimating. And we do this with volumetric measurements. Maybe you're using beakers or graduated cylinders. We do this with length measurements, okay? And actually, if you're using electronic balances or scales, maybe even to weigh yourself every morning, it's actually estimating your final digit. It's pretty dang accurate. It's pretty good, right? But it is still estimating that final digit for you. So how are we going to apply this? Well, before we get into the calculations, we need to actually be able to identify how many significant figures are present in a number. Okay, not every number is significant. And when I was in high school, my teacher just gave me a big old list of the 20 rules or so to identify significant figures and just said, memorize it, we're going to learn it the next day. But there's actually a way easier way to do it. Okay, and it's utilizing the United States, and it's a shortcut that works for absolutely every single number. So look at all these right here. We're going to solve a lot of these on the board here in a second, but first, let's discuss this using the United States of America. Here she is, in all of her glory. And what do we have on the west coast, just off the west coast of the United States? Well, we've got big water. Big water. And what is that water called? Well, it's called the Pacific Ocean, which we're going to just abbreviate P here for just a second. And then what do we have over here on the east coast? Big water. But what's that big water called? It's called the Atlantic, ladies and gentlemen. And that is what we are going to use to count the significant figures. The P is going to stand for present. The A is going to stand for absent. But what are we talking about here? we're talking about whether or not a number has a decimal place. If it has a decimal, it is present. If it does not, it is absent. And that's going to determine the direction that we come in from. Okay? So, let's bring up a couple examples. Slightly different look here as we tackle our first example of problems with significant figures and how to count them. So we'll start with the first 5 examples that you had on your plethora of values right before you. 4.0, how many significant figures are there? Just because there are 2 numbers there does not necessarily mean that all values are significant. If you look it up online, you're going to see terminology such as leading zeros and trailing zeros and non-zero numbers. That's all fine and dandy. There's a very easy way to do it though. Okay? And that is, when I look at 4.0, I see that there is a decimal point, which means it is present, which means I'm going to be coming in from the west coast, over here on the left, and that's the way I'm approaching it. I can only come in from the left or the right, Pacific or the Atlantic, present or absent. And what I'm going to do with each of these is I'm going to go to my first non-zero number, and that is because any number that is non-zero is always significant. Well, from whatever direction you're coming in, from the left or the right, you go to your first non-zero number. That number and everything after is always significant. It's as simple as that. Okay? So for my first number, 4.0, right, we're going to come in from the west coast, and we're going to go to that 4 because that's the first non-zero number that we see. It is significant, and everything after is also significant. We got 2 significant figures, and you're going, well, that's not a shocker. There's 2 numbers there. They got to both be significant. Well, not the case with the very next number. If we look at the next number, 3600, there is no decimal point, which means we're not coming in from the west. We're coming in from the east coast, right? Starting in Scranton, Pennsylvania, coming on in, and we're going to go to our first non-zero number, which means these first 2 zeros do not count. They are not significant values. They are what are called trailing zeros. 6 is the first non-zero number I have, which means 6 is significant, and everything after also is. And because I'm going from right to left, the 3 is after the 6, therefore it's significant. So this one also only has 2 significant digits, despite the fact that there are 4 numbers written. Now, what do you think about 5,000? No decimal point, which means, once again, we are coming in from the east, and we go to our first non-zero number. Well, we don't hit a non-zero number until our very last number, which is the 5. So 5,000 actually only has 1 significant digit. Then we look at 72.0. It's got a decimal point, which means we're coming in from the west, all the way from Malibu Beach in California with Miley Cyrus. Go to your first non-zero number, 7. The first number is non-zero. It is significant, and everything after is also significant, which means this guy has 3 significant digits. Okay? So then we look at 0.0036. Decimal point is present, so we still come in from the left, and I've got 3 zero numbers out front. None of them are significant. Only the 3 and the 6 are. So this also has 2 significant digits. So now, let's look at our others. Let's look at our others real fast. Holy moly, what an animation. Duh. How about that? How about that, ladies and gentlemen? Let's look at a few of these other values. So we just did the first 5 of these, right, that we had. And now let's look at some others. We've got 10,006. That looks a little different from the other ones that we've done. And here is where, if you're not understanding what's going on, you like these numbers. You like the numbers that have a non-zero number on the far left and on the far right. Why? Because any number that is sandwiched between 2 non-zero numbers is always going to be significant, because it doesn't matter if I come from the west coast or the east coast, I'm going to hit a non-zero number, which means all 5 digits here are significant. What about this next one? 45.0001, 0001, 3 zeros, right? I've got 6 digits, and they're all significant because everything is smushed between 2 non-zero numbers. The decimal point is present, which means we would come in from the west coast, we'd go to the 4, it is non-zero, and everything after is also significant. So every number here is significant. Scientific notation, you can use the exact same strategy, or you can just come to grips with the fact that anything to the left of this X in scientific notation is always significant. It doesn't matter if they put 100 zeros after this 3, it will always, they will all be significant. Okay? Which it's the same way if you were just coming across a number like 4.0. there is a decimal point, so you're coming in from the left, and everything after is always significant. 36.00, we've got a decimal point, so we're going to come in from the west coast. We hit a 3, therefore every number here is significant. All 4 numbers here are significant. We look at 600, there's no decimal point, so we come in from the east coast. We don't hit a non-zero number until we hit the 6, therefore there is only 1 significant digit here. And this is probably the most unique thing you can run into with counting significant digits. Just a point. There's no number after it, so why the heck did they put it there? Sometimes we need an extra significant digit. What do you mean by that? Well, imagine if this decimal point wasn't there. If it wasn't there, it'd be absent, and we'd be coming in from the right coast, and there would only be 2 significant digits. However, because it is there, we're coming in from the west coast, and we're going to hit the 2 first, and everything after is always significant. So 250 has 2 sig figs, but 250 point has 3 sig figs. Spicy, spicy.
So now let's get a little extra practice learning how to count significant figures using the same number written 4 different ways. Look at my very geographically accurate United States of America. We still have the Atlantic Ocean on the east coast and the Pacific Ocean on the west coast. But notice, it's 200, just written 4 different ways. We have 200, 200 with a decimal, 200.00, and 200 in scientific notation, 2.0 times 10 to the second. And each of these have a different amount of significant figures, which indicates that each measurement has a different level of accuracy. You can't just add extra zeros on the end of a measurement just because you want to. Every zero that you add on the end of a measurement indicates a higher level of accuracy. So let's count our significant figures to find out who the most accurate measurement is. Remember, we're always going to use the rule present or absent. Is there a decimal point or is there not? And in our first number, 200, there is no decimal point, which means we're going to come from the east coast. We're going to come from the right, okay? So starting up here in Scranton, this is more New York and Maine area, coming in from the east coast, we're going to go to our first non-zero number, crossing out any zero that we hit along the way. 0, 0, and the last number we hit is our first non-zero number, which means there is only 1 significant figure here. 1 sig fig. Next, we go to 200 point, and it's present, which means we're going to come from the west coast. We're going to come from the the Oregon-ish area, Northern California, whatever you want to rock with here. Go to your first non-zero number, and the first number we hit is non-zero. We know that that number is significant, and everything after is also significant. So actually, all 3 of these guys are significant. That one has 3 sig figs. Next, 200.00. Decimal point is present, so we're going to come from the west coast. Now we're in California. Go to your first non-zero number, and everything after is also significant. So actually, all 5 of these values are significant. And then with our last number, scientific notation, do not think of it any differently. In fact, it's even easier. Anything to the left of this X is always significant. But you can still use that decimal point rule, present or absent. It's present, which means we're going to come from the west coast. Therefore, it has 2 significant figures. So scientific notation enables us to write certain numbers that wouldn't be able to be written with a certain level of significant figures. It allows us to do that, so might need to exploit that at some point in the future. But pay attention, each of these 4 different ways of writing 200 has a different level of accuracy. Who is our most accurate measurement? Obviously the one with the most significant figures. This is not just 200. This is exactly 200 to the hundredths place. This guy, they might just be estimating that it's 200 or around 200, might not even be there, okay? So every time you're adding a 0 on the end, you are adding a greater level of accuracy. Now we are going to practice rounding values to the appropriate number of sig figs, and this is going to apply whenever we're actually doing calculations with measurements. Maybe it's numbers that you gather in the lab, or maybe it's numbers that we provided for you. Either way, we're going to round the following number, 1974.2965, to each of the following amounts of sig figs, okay? So 1 through 7. And there's a little trick that I like to do with this. Let's say we're rounding to 1 sig fig. Well, what I'm going to do is I'm going to underline the first significant figure, because it's the next number that is going to determine whether or not I round up or stay the same. And rounding rules, except for that perfect 5 rule that we just discussed, there's not really anything to worry about here. Then it's just am I rounding appropriately? So 9 is obviously greater than 5, so this one is going to round up. However, we are not just going to leave this 2, and a lot of kids make this mistake here in the beginning. Keep in mind, what place value was this 1 in? It was in the thousands place. The point of rounding is not just to condense it to a certain amount of numbers, it's to maintain as close to a value as we possibly can. And so, we are not just going to leave it as 2, even though this is 1 sig fig, but we're going to make it 2,000. Do not lose value when rounding. We're going to save 2 for last, because that's going to involve one of the more obscure concepts with rounding with these sig figs, so we're going to save that for last, and let's move on to 3. Okay? So, if we're rounding to 3 sig figs, we're going to underline the first 3, and we're going to draw an arrow to the 4th to see if that is going to cause us to round up or stay the same. Well, 4 is less than 5, so we're absolutely going to stay the same. But what value is that 7 in? Like we just did with the first example, a lot of kids, when they're first starting out in chemistry, would make this mistake and leave it as 197. But it's not that, because the 7 is in the tens place. Therefore, you are missing a 0. Do not forget that 0. Okay? Next, let's go to 4 sig figs. Okay? We've got a 2 after the 4, therefore we're just going to stay the same. So this one is as simple as it gets. We're just rounding this to the ones place, 1974. Next up. The 9 is going to cause our 2 to round up to a 3, so we get 1974.3. And after you write your number, just double check. Does it have the correct number of sig figs? And you can use that present or absent rule to double check yourself. Now we go to 6 sig figs, so we're going to extend our line and draw our arrow to the 6. The 6 is going to cause our 9 to round up, and that 9 is then going to cause, when the 6 causes the 9 to round up, it becomes a 10, which carry the 1 over to the 2. So this 2 is going to become a 3. Just like you learned how to do whenever you were doing addition and subtraction in elementary school. However, if we leave it like this, that's only 5 sig figs. So what can we do to add a 6th significant figure here? Just don't forget that 0. Okay? Now we go on to 7 sig figs. And we run into that very rare, very obscure, perfect 5 rule. Okay? Remember, we love even numbers, we don't like odd numbers. So, because this last number is a 5, and there's nothing after it, the number that we're looking at to indicate whether or not this is going to round up or stay the same, there's nothing after it. If it was followed by 0, 0, 0, 0, 0, 1, it is no longer a perfect 5. The last number that you're looking at has to be a 5 with nothing else after it. Okay? So, we're running into that. If we were to round this 6 up, 6 would become a 7. Newsflash, 7 is an odd number, which means this guy's going to stay the same, actually. Very weird. But our final rounding here, 1974.296. Do not round it to a 7. Let me write that down here so it's a little bit easier to read. That 6 will not become a 7 because a 7 is an odd number. Okay? Very obscure. Going to happen very rarely. So now let's go back to 2 sig figs. Okay. We're looking at the 7. 7 is going to cause my 9 to round up, and the 9 is going to turn into a 10, which carries over to the 1, which means, once again, our value is 2,000. How do we make 2,000 and 2 sig figs? That's the question. Some of you might be suggesting, let's just put a decimal point at the end. But if you count your sig figs, now it has 4 sig figs. That's not going to work. Some of you at home might be going, oh, just put the decimal in the middle, you idiots. Well, for one, now it's a totally different number. Now it's 20.00, and still 4 significant figures. So you're brainstorming. The only way you can do this is utilizing scientific notation. Remember, we mentioned that scientific notation enables us to sort of get the exact number of sig figs that we want with any number. Because anything written to the left of the x in scientific notation is always, always significant. 2.0 times 10 to the third.
Quarantine log, day 212. I'm so far removed from any socialization that when I finally summoned up the courage to have a pizza delivered to my house, and the pizza guy, his name was Tom, said, "Enjoy your pizza." I said, "Thanks, you too." He didn't have a pizza. So broken.
We've learned how to count sig figs, we've learned how to round with sig figs. Now let's learn how to round with sig figs in calculation, as that's what we're actually going to be doing in chemistry and in the lab. Well, there's slightly different rules with significant figures as it pertains to addition and subtraction versus multiplication and division. Two different worlds of math, right? Addition and subtraction, when we are faced with an operation like this, we are going to round to the same number of decimal places as a measurement with the least amount of decimal places used in the problem. What does that mean? Well, if we see this example right here, 4.5008 has 4 decimal places, and 4.43 has 2 decimal places, we are only accurate to 2 decimal places. Remember, we are only as accurate as our least accurate measurement, which means we are going to be forced to round this guy to 2 decimal places at the end. Whatever the least amount of decimal places used in the problem is, that's what you have to round your answer to. And so we're going to utilize that same logic in tackling a couple of example problems down here, which we can go ahead and mentally prepare ourselves for how many digits are going to be in our rounded answer before we actually take it to the board and solve it. 4.2 has 1 decimal place, 12.89, 2 decimal places, and 234 no decimal places, which means in our answer we will have 0 decimal places. Can't have any. Our least accurate number, our least accurate value here, didn't have any decimal places. Next problem, 12.300, 3 decimal places, 64.50, 2 decimal places, 0.023456, 1, 2, 3, 4, 5, 6 decimal places. We can only round our answer to 2 decimal places, right? It doesn't matter if one of your values goes to the 100th decimal place. It doesn't matter. You can only go to the least amount of decimal places used in the problem. So punch whatever the exact numbers are in your calculator and then just round it to the correct number of decimal places, just as you did in our last operation. Either way, we'll take it to the board.
Now we're looking at calculations with sig figs, with addition and subtraction. Subtle different rules between addition and subtraction versus multiplication and division. The rule with addition and subtraction is we are going to round our final answer to the least amount of decimal places used to get there. So looking at our first example here, we have 4.5008, 4 decimal places, minus 4.43, 2 decimal places. So in the end, we get our full answer in the calculator, 0.0708, but we're going to round to 2 decimal places because that's the smallest amount of decimal places used to get there. So what they did is they underlined their first 2 values here, and they look at that third number to see if it's going to round up or stay the same, and of course it stays the same here. So what we're going to do with our next couple of examples that are in your notes, we're going to plug it in, and we're going to write down exactly what the calculator tells us, and then we're going to round. So for this top number, we get 251.09. This number has 1 decimal place. This number has 2 decimal places. This number has 0 decimal places, which means we are going to round to the 1's place. We're going to round to 0 decimal places. So 251.09 simply becomes 251. Moving on to the next one, 12.300 plus 64.50 plus 0.023456. Very long decimal here for no reason. 8, 2, 3, 4, 5, 6. That's the whole number we get, but this guy has 3 decimal places, this guy has 2, and this guy has 1, 2, 3, 4, 5, 6. So we're going to round to 2 decimal places because that's the smallest amount used. So underline our first 2. 3 stays the same. 76.82 is our final answer.
Multiplication and division, in my opinion, are even easier because we're not considering decimal places. We're going to round to the least amount of sig figs utilized in the problem, period. So when I look at this problem right here, 4.2 times 3, well, 4.2 has 2 sig figs, 3 has 1 sig fig, which means I'm going to round to one significant figure. I'm only as accurate as my least accurate measurement, which this is going to feel really weird, especially if you're getting into really, really large numbers that you're calculating with. You might be rounding like several thousand values away from what the number shows in your calculator. It's weird. It's counterintuitive to a lot of us, and yet we must do it. We are only as accurate as our least accurate measurement. So before we take these next couple to the board, 45.89, that's 4 significant figures. 3.45 has 3 sig figs, and 6.7 has 2 sig figs. So what are you going to round this to? 2 significant figures, the least amount of sig figs utilized in the problem. 12 divided by 4.5, they both have 2 sig figs, so there's nothing to worry about there. You're going to round to 2 significant figures. And then this number right here has 1, 2, 3, 4, 5 significant figures divided by 1, 2, 3, 4 significant figures. Therefore, your answer will have 4 sig figs, least amount of sig figs utilized in the problem.
Next, we're looking at the rules of the multiplication and division, which in my opinion, slightly easier. We're not paying attention to the least amount of decimal places. We're paying attention to the least amount of sig figs, period. And this is the rule that applies to almost every single calculation with chemistry moving forward throughout the entire course. So let's look at our first example. 4.2 times 3, in the calculator gives you 12.6, but if these are measurements we took in the lab, we are only as accurate as our least accurate measurement. Okay? So we have to round to the least amount of sig figs utilized. This guy has 2 sig figs. This guy has 1 sig fig. Therefore, our answer can only have 1 sig fig. So when I get 12.6, I'm going to underline the first significant figure and see if that 2 rounds me up or stays the same. And I obviously stay the same, but I can't drop the value. This 1 is in the tens place. So my answer is actually 10. And if we're looking at the example in our notes, the units here were centimeters. Centimeters times centimeters is centimeters squared. Next example, 45.89 times 3.45 times 6.7. We get 1060.74735. Lots of decimals, but we can't leave it that way. 4 sig figs, 3 sig figs, 2 sig figs, which means our final answer can only have 2 sig figs. So we're going to underline our first 2 significant figures, which just so happen to be the first 2 numbers, the 1 and the 0, and that 6 is going to cause my 0 to round up. But please, please, please do not leave your answer as 11, because where is that 0 located? It's located in the 100s place. Sorry, the hundreds place. Therefore, our answer is 1100, and our units on this one are meters cubed, since those were all meters from the get-go. In our final example here that is in our notes, 0.089930 divided by 3.892, we have, don't mistake this 0 as significant. It's present, so we're coming in from the left. We only have 1, 2, 3, 4, 5 significant figures divided by 1, 2, 3, 4 sig figs. So our answer is going to have 4. And so the number we get in here, the unrounded number we get here, is 0.023106372. Lots of decimals here, but we can only round it to 4 sig figs. And here's where a lot of kids are going to make a mistake. This 0 is not significant. Therefore, he does not count in our 4 sig figs. We're going to go all the way to that 6. And that 6 is obviously going to cause my second 0 to round up. So my final answer becomes 0.2311. And there were no units attached to this question. There will always be units whenever you're doing measurements in a lab or such like that. So always pay attention and mind those units.
Well, what do we do if we're faced with multiple steps? As we know, in the real world, calculations aren't always just one step. Well, if you've got multiple operations that are a mix of addition, subtraction, multiplication, and division, there is a way to do it. Ideally, we are only rounding once. Every time you round, you're making your answer less accurate. And so this causes a weird shift in your brain that you have to do here. Okay? It's more difficult to explain, easier to practice, and put the pencil to your paper, that sort of thing. You can look it up online, and a lot of sources will say that you should round after each step appropriately. But like I said before, every time you round, you're making your answer less accurate. So we're going to try to avoid that. Of course, we know about PEMDAS. Almighty PEMDAS, the order of operations. We're going to follow that, absolutely. But we have to round in our brain without actually rounding on paper, if you catch my drift here. So if I were to look at this operation by itself, 215 plus 85.15, it's addition, which means we're going to round to the least amount of decimal places used in the problem. So that would be 0. 215 plus 85.15, it would just round to 300. However, to make my answer as accurately as possible, because I'm going to get 300.15 out of my calculator here, I'm going to make sure that I use that 300.15 in the next step. However, I am also realizing that this would have had 3 sig figs if this operation was on its own. Okay? And we are going to have, 3 sig figs here divided by 1, 2, 3, 4 sig figs, which means our answer will only have 3 sig figs. And what we're going to show you on the board is that if we round after the first step, we're going to get different answers in the end. And that could cause issues in the real world, not to mention assignments. An easier way to do this, the trick that you can typically use with problems like this, is just look at your least amount of sig figs used in the problem, period. Okay? Just like the multiplication division rule. This guy's got 3 sig figs. This guy has 4. This guy also has 4. Therefore, we're going to round our final answer to 3 sig figs. Most of the time, you can absolutely do that, okay? Just try to keep track of what you're actually plugging in your calculator and keep track of the operations. Either way, not so bad. Let's solve it on the board.
So utilizing sig figs whenever you're doing a math problem that involves multiple operations, especially different types of operations, can be kind of tricky. If you look it up online, you might get different processes here. Some say to round after every step. In doing that, you're making your final answer less accurate each time. So we're actually going to solve this problem rounding after each step and not rounding after each step, and you're going to see how it influences your answer either way. What I'm going to say to do is round once. Round when you're getting your final answer. Now, the stipulation with that, though, is that we are going to mentally act like we are rounding after this first step. Looking at the first step, of course, whatever's in parentheses is an addition problem. And the rule with addition in sig figs is to round to the least number of decimal places used to get there. So 215 plus 85.15, yes, this is going to equal 300.15 in my calculator. However, if this were an addition problem that stands on its own, I would just round it to 300 because this has no decimal places and this has 2 decimal places. However, if I round it to 300 and then plug it in, I'm going to get a different answer where if I were to use 300.15, the full number, and then divide by 0.04678. So what I'm going to do in my head is I'm going to track that this should be 3 sig figs after this step. But I'm not going to round. I'm not going to round until the very end. Okay? So 300.15 divided by 0.04678 gives me a final answer of 6,416. And we're just going to give you several decimal places here. 6416.2035. Okay? Now what we need to do is, because our last operation was division, we're going to round to the least amount of sig figs involved, or the shortcut here is just look at the least amount of sig figs utilized in the problem. And technically that's this one right here with 3 sig figs. Remember, technically after this first step that we did, mentally, we told ourselves that we only had 3 sig figs here, even though we used the full value. So actually what we're going to do is we're going to round this guy to 3 sig figs, which means our final answer is 6420. But let's say that we went ahead and rounded this off to 300 and then plugged it in. And let's say it's got that full 3 sig figs. Let's plug it in now. Notice we get 6412.997. Well, this is still going to get rounded to 3 sig figs. Just notice that we get a different final answer. We get 6410. And maybe whatever situation you're doing this in the real world, it doesn't really matter. how close you are. Maybe, a difference of 10 isn't that big of a deal. However, I'm going to say that this is the true correct answer because I only rounded once. And by only rounding once, that's making my answer as accurate as possible. So round once, it's kind of weird to track. The shortcut that I always implement is knowing that I'm going to end with division. The rule is round to the least amount of sig figs, period. Well, just look at the least amount of sig figs utilized in the problem. Right there, 3. My answer is going to have 3 sig figs in the end.
In my opinion, this next part is the most difficult concept to grasp in Unit 1 of Chemistry, dimensional analysis, and it is so important to grasp because we're going to utilize it frequently all throughout this course. Dimensional analysis is a fancy way of saying that we're going to be doing multiple mathematical operations to convert one unit or one substance to another unit or substance in the end. It's just different, it's conversions to look at something a different way, okay? Dimensional analysis. And what we are going to utilize is what is called the train track method, okay? I think it's just cut and dry the best method of doing this. It's a great way of showing your work, keeping yourself accountable for your work, and if you're following the steps diligently, you're going to know when to stop, and you're going to know exactly how to tackle every problem. And so for these next couple of examples, we're going to read these really fast, then we're going to quickly translate to the board. You want to practice showing your work on these, okay? There's multiple ways to do it, but you want to practice showing your work the way that we're showing you how to do it right now. Example 1, you know that there are 12 donuts in a dozen. How many dozens of donuts do you have if you have 85 donuts? I know you guys are smart. I know that all you simply need to do is 85 divided by 12, okay? Because there's 12 donuts in a dozen, and we're trying to make the smaller thing into the bigger group, so we're going to divide by how many donuts are in a dozen. But we're going to show it a slightly different way. We're going to use dimensional analysis. We are going to cancel out the unit that we are starting with and end with the unit that we would like to, which is dozens in this case. Example 2, a little bit more complicated. You've lived on this earth for 4 decades. How many seconds have you lived, right? Once again, you can probably figure it out. And yes, you could just go to Google and say how many seconds are in a decade, but that's boring, right? But you know all the conversions. It's more than one step, but you could still do it. So we are going to draw out the train track with multiple steps as well. Keep in mind, these are all calculations. Therefore, we are going to round our answers to the least amount of sig figs provided to us in the problem. We are only as accurate as our least accurate measurement. It just so happens that the only measured values in each of these problems are the numbers that they provide for you. And that's always the case with these dimensional analysis problems. The number that they start you out with is how many sig figs will be in your answer. So 85 donuts has 2 sig figs. Got around to 2 sig figs. And then example 2, kind of weird. You've lived on this earth for 4 decades. Is it exactly 40 years? I don't know. Let's just say it's 1 sig fig regardless. And we're going to round this guy to 1 sig fig. Either way, let's solve it.
Now that we have sig figs in mind and calculations with sig figs in mind, let's see how we can practically use them. And this is a technique that you are going to use throughout this course. So please do pay attention on the setup for this. This is called dimensional analysis. And what we're going to utilize is something that looks like a train track. So as you might hear some teachers call it the train track method. But what it really is a gigantic fraction where you're starting from one unit and you're converting to another unit, okay? Gigantic fraction. So let's look at our first example with this. You know that there are 12 donuts in a dozen. How many dozens of donuts do you have if you have 85 donuts? This is a very simple mathematical operation. All I have to do is 85 divided by 12. I know that. But let's set it up the way that we're going to implement with all the future problems in this course, or sorry, in this unit. So we're starting with our 85 donuts, and what you're going to do is you're going to write that in the top left of wherever you're working every single time, and you're going to draw a line. All right, so it gets its own little box there. And what we want to end with is dozens, because I want to know how many dozens this amount of donuts is. Well, this is one gigantic fraction. Numerator on the top, denominator on the bottom. And what I'm noticing is that donuts is not dozens. Therefore, I do not want it to be around whenever I'm getting to my final answer. Therefore, I have to get rid of it. How do you get rid of something in a fraction? You put the same thing on the top as you do on the bottom. So what I need to do is I need to have donuts on the bottom. And what do we know about donuts? Well, we do know how many donuts are in a dozen. So dozen is going to go up top. And I know they're not exactly written correctly, dozen versus dozens, but that is the same unit, correct? So we're canceling out donuts. Now we've got to ask ourselves, what ratio, what proportion can we relate dozens and donuts? Well, a dozen, a singular dozen, is 12 donuts. Pay attention to that. Okay, the 1 is always going to go next to the bigger unit. Very, very, very important. And so now, once this matches what I'm going for, I'm done. Now I can plug it in. And what you're always going to do is you're going to multiply your top and you're going to divide by your bottom. So here, technically, what's occurring in your calculator is 85 times 1 divided by 12, which, of course, is just 85 divided by 12. So now, our final answer that we get in our calculator is 7.08333333 repeating. What are we going to do with that answer? Well, we have to pay attention to sig figs. The only thing that is going to matter to your sig figs is the initial value that they are giving you. The only things that impact sig figs are measured values. This is a fact, a factual statement. 1 dozen will always equal 12 of whatever you're talking about, so that's never going to change. These do not contribute to your sig figs, but this 85 does. Someone went out there and counted those. So that's 2 significant figures, which means my answer needs to have 2 significant figures. That's kind of the golden rule for the rest of this, this unit and this course, really. However many sig figs you start with is however many you want to end with. So you don't have to be as nitpicky with the rules as we were just teaching you. So I started with 2 sig figs. Let's round this guy to 2 sig figs. So my real answer is 7.1 dozens. Okay, simple enough. Our next example is going to require multiple conversions, though. Example 2 reads, you have lived on this earth for 4 decades. How many seconds have you lived? Wow. That's a lot of seconds. And I'm sure Google could do this work for you, but you can also do it. So we've lived on this earth for 4 decades, and let's just say that that's 1 sig fig. And we're drawing a long line here because we know we're going to need multiple conversions. Okay? So you got seconds right there. Now, I don't know how many seconds are in a decade. What I do know is that decades is not seconds, therefore I need to get rid of it, which means the next place I need to see decades is on the bottom. What do I know about decades? Once again, I don't know how many seconds are in it, but I do know how many years are in a decade. So let's go ahead and do that. Now, this is what we said in the last problem. The 1 is always going to go next to the bigger unit. So ask yourself, which one is bigger, a decade or a year? Obviously a decade. And there's 10 years in a decade. And so what we're doing as we're moving along is we're seeing our units cancel out until all we're left with is our intended unit, seconds. Now, I don't know how many seconds are in a year. I do know that I got to get rid of years. So I'm going to send that to the bottom. Now, I don't know how many seconds are in a year. I do know how many weeks are in it. I know how many days are in it. Let's get super specific here. Let's go with days. And in every year, because a year is bigger than a day, how many days are there? 365 days. Technically 365.25, we won't get too nitpicky. I don't know how many seconds are in a day. I'm sure Google could answer that. We're going to send day to the bottom. And I know how many hours are in a day. And there's 24 hours in one day. But notice, every time we move forward, these units get canceled out. So you can kind of see where we're going with this. Right? And if you don't know how many seconds are in an hour, well, you can break this down even more. In every hour, there's 60 minutes. Right? Hour, hour. And then in every minute, there's 60 seconds. And so we're finally in that final unit, seconds, and we need to plug everything in. Wonderful news is there's only numbers on the top that I care about because the bottom is entirely comprised of 1s. So all I got to do is multiply straight across the top. Let's put it in scientific notation. Let's just say we started with 1 sig fig. Let's end with 1 sig fig. So my final answer is 1 times 10 to the 9th power. Unrounded, it's like 1.3 or so. But there we go. Dimensional analysis. Now we're going to apply this to the metric system.
So we are not always going to be doing calculations with donuts and custards and seconds. Sadly, I wish we were. But in chemistry, it's more pertinent to use chemical units, or, if we're actually making measurements in the lab, metric system. Here in the United States of America, we use what is called the imperial system, sometimes called the standard system, which doesn't make a whole lot of sense, seeing as it's us and only 2 other countries that use it. That's pretty crazy. That's for a number of reasons, but the metric system does a whole lot of things a lot better. It's a very, very simple to understand system that's all based on the number 10, whereas the imperial system that we utilize is all over the freaking map, right? Just really depends on what you're looking at, okay? So let's look at our metric system units here. We're going to point out something that's very, very important and unique, right? We've all heard of the meter for length. Here's the weird part. Mass. We would expect that the base unit for mass would be the gram, and the gram is the base unit. However, it's not the standard unit. The standard unit for mass is not the gram, it's the kilogram. In fact, if you're looking at this thing, it's the only one with a prefix attached to it. Everything else is just the unit. Why'd they do that? Well, it's because if we were weighing everything with grams, our numbers would get really big really fast. Imagine you're getting on the scale every morning and you see that you weigh many thousands of grams. How do you feel about yourself right now? Not so good. And so kilograms, it's a more efficient way of reading these values, right? A gram is so tiny that we're going to just go ahead and say that the standard unit for mass is the kilogram, okay? Keep that in mind. Everything else is just the unit without the prefix, but the standard unit for mass is the kilogram. The base is the gram. Everything does revolve around the gram, but it's not the standard unit. Time, seconds, electricity, we're not going to deal with in chemistry, but there it is for you. Temperature, Kelvin, we'll talk about this a little bit later in this unit and the next unit and several other times in the course. Kelvin might be new to you, but it's nothing to be afraid of, right? It's just a different way of looking at temperature. And then quantity, the mole, not important to this unit, but very, very, very important later on down the line in chemistry. And it's just a way of measuring how much stuff that we've got here. And then lumina intensity, don't worry about it. Won't be in chemistry. Either way, let's look at a few other units here. Derived units, meaning that they combine units from the previous slide to make other ones. Volume, we're going to see a crap ton of. Density, we're going to see quite a bit of in this unit and the next. And then speed, more of a physics concept, but you got to know what you're doing here, right? So either way, with this new metric system, we are now going to utilize metric units to convert from one unit to another, right? I'm not going to take my cell phone and weigh it with kilograms or hectograms or yottograms. Why? Grams is probably the best option. There's not much stuff there, so why wouldn't I use the most efficient number of looking at things, right? And so what we're going to utilize is a metric unit conversion chart here. You can find the link that you can find the conversion chart that I use just below this video. So feel free to consult that if you don't already have one on your own. But either way, we're going to look at the following example problems. And we are going to either have a one-step conversion or a two-step conversion. And here's the deal. Here's the mental that you got to work with here. Our base units, which are the meter, the gram, and the liter. Meter for length, gram for mass, liter for volume. Those are the three main ones you're going to do this with. However, you can put prefixes on any of those metric units that we were talking about before. But either way, everything on your metric conversion chart revolves around the base unit. If I look at example 1, and I see that I'm converting from a unit that is not the base unit to the base unit, it is absolutely a one-step problem. If your base unit is at the beginning or the end of your train track, it is one step. Look at example 3. I don't see the base unit. I've got kiloliter and I've got milliliter. I do not see liter. So that means that this is a two-step problem. And that is the most amount of steps you should be doing with these metric conversions. Let's go to solve them on the board.
Now we're going to work out some of these metric system conversions, which is the main way that we're going to implement dimensional analysis at this point in chemistry. A little bit later on down the line, we're going to actually rope in some chemistry content with it. But now this is a great place to start. And what you're going to need for this is you're either going to need to memorize and internalize metric conversions and their prefixes, or you're going to need a conversion chart on standby right next to you. Either way, the metric system all revolves around these base units, okay? And what we're going to focus on are the meter, the liter, and the gram. Gram for mass, liter for volume, meter for length. Those are the main ones you're going to do. Anything without a prefix is the base unit. And all you have to do is slap on a prefix and now become something new, right? centimeter. There's 100 centimeters in a meter. Therefore, a meter is 100 times bigger than a centimeter, or a centimeter is 100th the size of a meter. That sort of thing. So now we're simply going to convert them from one unit to another. Okay? So now it's the same process with the donuts and the seconds and the years. Millimeters is not my answer. So where's the next place I'm going to see it? Well, you're going to send it to the bottom. But before we start, let's take a look. Take a look at the similarities in this problem. Take a look at the dissimilarities of this problem. So right here, we're ending with meters. We're starting with something that's not meters. We're ending with meters. That means we're ending with the base unit. In this problem, we're also ending with the base unit. But this third problem is unique. We are not starting or ending with the base unit. And the thing is, with this metric system, with everything revolving around the base unit, the maximum amount of steps that you should be implementing in your conversion, in your train track, should only be 2 steps. Because the base unit should be involved in every single step. You're either converting away from the base unit or you are converting to the base unit. Either way, the base should be involved every single time. If you don't, you're putting extra work on yourself. You're either memorizing the entire conversion chart and all of the relationships and connections that are there, absolutely no need for that, or you're going too far and you're going to get the wrong answer. So let's take a look at this. Millimeters to meters, either way, millimeters is not in my answer, so I'm going to send it to the bottom. And meters is going to go on top because I can convert from anything to the base unit. Base unit has to be involved. And this is where size matters. I know in other aspects of our lives, they tell size doesn't matter. In science, size matters, people. Okay? So ask yourself, which one is bigger? A meter or a millimeter? So maybe you've memorized this, maybe you haven't. Either way, look at your conversion chart. And a meter is bigger. And whichever unit is bigger, you put a 1 next to it. Now, how many of that smaller unit fit into a meter? Well, there's 1,000 millimeters in a meter. Is this the only way you can write this out? Absolutely not. There's multiple ways you can do this. This is just what I think is the simplest way. Now that meters matches meters, we're good to plug it in. As we said before, the only number that should be dictating how many sig figs are in your problem is the starting value. So all of this in the middle, because these are factual conversions, they do not dictate your sig figs. So I started with 3 sig figs. I need to end with 3 sig figs. So you got your handy dandy calculator on you, 75.3 divided by 1,000, right? Double check yourself just to make sure you don't get anything wrong on your test. And we get 7.53 times 10 to the negative second. Or if you want it out of scientific notation, we can do 0.0753 meters. Don't have any naked numbers. All right, moving on to the next example. Now we're dealing with mass, kilograms to grams. So now, kilograms is not my answer, so I'm going to send it to the bottom. And I can convert from any prefix unit to the base unit, and the base unit here is grams. So grams is going to go on top, and a kilogram is bigger, so a 1's going to go next to him. Now, how many grams fit into a kilogram? If you haven't memorized it, look at your chart. There's 1,000 grams in a kilogram. So all this is 54.2 times 1,000. So 54,200 grams, or 5.42 times 10 to the 4th grams. Whatever floats your boat, whatever your teacher wants. And the very last one, remember, our line's a little bit longer because we're going to need an extra step because we didn't start with liters and we didn't end with liters, which means we have to go through liters to get to our destination. Kiloliters is not my answer, therefore it has to go to the bottom. And what unit is going to go on top? Not milliliters, it has to be the base unit. The base unit must be involved in every single step of these problems. So liters is going to go on top. Now we ask ourselves, which one is bigger? Kiloliters are. And there's 1,000 liters in a kiloliter, just like this step right here. 1,000 grams in a kilogram, 1,000 liters in a kiloliter. But we're not done because this does not match this. So now liters is going to go to the bottom. And milliliters is going to go on top. Now we run into the exact same conversion over here, just flipped, because a liter is bigger, and there's 1,000 milliliters in a liter. So now, milliliters matches milliliters, so we're good to go. We can just plug it in, 6.7 times 1,000 times 1,000, and we're going to double check in our calculator so we don't get it wrong. and look foolish on camera. And if it gets to be a bigger number, I would say over the 10,000s place, I would go ahead and put it in scientific notation. Your calculator is doing it for you anyway. 6.7 times 10 to the 6th power.
Because dimensional analysis is treated as one big fraction, we shouldn't be scared of problems like this. They look a little different, look like how we're going to have to approach it a little bit differently. Not at all. Because our dimensional analysis, our train track, is already a fraction, and now we have units that are set up as a fraction, well, why don't we just put the numerator unit on the top and the denominator unit on the bottom? Changes absolutely nothing about it. And so these double unit problems, while they might take more steps, are the exact same process. So let's solve them on the board.
Now looking at the double unit problems of dimensional analysis, examples 4 and 5 in your notes if you're following along, it asks us to convert 435.6 milligrams over milliliters to kilograms over liters. It looks more complicated, but the work is the exact same. Remember that our train tracks that we draw out are gigantic fractions, so why don't you abuse that? If your units are a fraction, then why not put the units as a fraction here? So instead of putting them both in the numerator, we're going to put the numerator part of the fraction in the numerator and the denominator part of the fraction in the denominator. Wow, what a concept. And what we can do is we can ignore one of the units until we're ready for it. So let's just convert milligrams to kilograms first. Let's do the numerator part. So milligrams needs to become kilograms. Either way, it's not my final answer, so I'm going to send it to the bottom. Got to get rid of it. And remember, we have to involve the base unit in any step. Now we ask ourselves, which one is bigger? A gram is bigger. And there's 1,000 milligrams in a gram. Grams does not match kilograms, so we're not done yet. So we're going to send grams to the bottom. And kilograms is going to go on top. Ask yourself which one is bigger, and a kilogram is bigger. And there's 1,000 grams in a kilogram. So now this matches what I'm going for, so I'm done with the numerator part of my units. Now let's deal with milliliters. Milliliters to liters is a very simple step, except one little curveball here. Where is the milliliter starting? If I need to get rid of it, where is the next time I'm going to see milliliters? Is it in the bottom or is it in the top? And the answer is it has to be in the top because it's already here in the bottom. In order to get rid of a unit, you have to see the same thing on the top as you do on the bottom. And as of right now, it's already on the bottom. So let's send milliliters to the top here and liters to the bottom, which is exactly where we want it to be. Ask yourself which one is bigger. A liter is bigger, and there's 1,000 milliliters in a liter. So now your units that you're going for match up. We've got liters on the bottom, we've got kilograms on the top, so we're good to go there. All you gotta do is plug in your calculator. And if you're really, really smart, then you can see that a couple of these thousands cancel each other out. Just make sure that because we started with 4 sig figs, we need to end with 4 sig figs. So this is just 0.4356 kilograms over liters. Now let's take a look at our next one. This is one where we really want to pay attention to those sig figs. We're starting with 2 sig figs here, so we want to make sure that we end with those 2 sig figs. And the reason why, the metric system usually does it for you, because all you're doing is you're moving the decimal place side to side, essentially. But when we're going from hours to seconds or vice versa, you're multiplying by numbers or dividing by numbers that are not 10. You're multiplying and dividing by integrals of 60, okay? So we're going to make sure that we double check and pay attention to that, but either way, we're going to solve it the same way. Let's solve kilometers to meters first. Kilometers is going to go to the bottom. And we can go from any prefix to the base unit. Ask yourself which one is bigger. In every kilometer, there's 1,000 meters. So this one's already good to go. Now I got to convert hours to seconds. Remember, to get rid of hours, I have to send it to the top. Maybe you know how many seconds are in an hour. Let's just say you don't. In every hour, there's 60 minutes. Like so. So now your hours are canceled out. And in every minute, there's 60 seconds. Like so. So now we get 6.7 times 1,000 divided by those 2 sets of 60s. And what we get is 1.8611111 repeating meters per second. We started with 2 sig figs. We need to make sure we end with 2 sig figs. So my final answer should be 1.9 meters per second.
Quarantine log, day 213. I have filmed a lot of these videos. I now have retinal scarring. Please let me out of my house. Wear a mask.
Really quick concept here, and it's how to convert temperature to Kelvin. We're not going to be utilizing Fahrenheit in the class, even though that's, if you're in the States, that's what you're typically accustomed to. If anything, you're going to be given it in Celsius or you're going to be given it in Kelvin, and you need to be able to interchange between them. Well, all Kelvin is a measurement of essentially the theoretical coldest temperature that you could possibly get. And that is what is known as absolute zero. Absolute zero is not 0 degrees Celsius. Absolute zero is the point at which molecules have zero kinetic energy. And if you're at 0 degrees Celsius, that's just the point where water freezes. So it's certainly not where they have zero kinetic energy. Solids still do have kinetic energy, but at absolute zero, which actually turns out to be negative 273 degrees Celsius or so, that is the point that is theorized in which molecules will have zero kinetic energy. And so Kelvin is simply a way for us to measure that. We are frequently at 0 degrees Celsius in our calculations, and we can't do math with the number 0 typically. And so, if we are in Kelvin, we'll never be at 0, because actually, we've never literally gotten to absolute 0 here on planet Earth. We've come very, very close. They've come within 1 Kelvin of such, but they've never actually gotten to absolute 0, aka negative 273 degrees Celsius. Therefore, the way to calculate this is simply to add 273 to your Celsius, and it becomes Kelvin. And so, 0 degrees Celsius is simply 273 Kelvin. 40 degrees Celsius plus 273 becomes 313 Kelvin. And if you wanted to convert back to Celsius, all you got to do is subtract 273. Not so bad, right? Last concept of the day, we're going to be looking at density. And you've probably seen this formula. Density is mass over volume. How much stuff have you crammed into your space that you have before you? Okay? A couple of things to look at here before we actually get into the calculations here. One of the very important things that you need to understand is that 1 cubic centimeter is equivalent to 1 milliliter. You'll see them used interchangeably in the problems here. And we have direct means, and we have indirect means. Typically, you can utilize direct means for finding the mass or the volume of an object, aka if you've got a cube, you can simply put it on a scale to get its mass, and then maybe you can use a ruler to measure side times side times side to get its volume. But what if you've got a really weird object? Let's say someone has just upset you to no end. Like you're going off the deep end. You get angry, and all of a sudden you've got this human being shaped object at your doorstep. I don't know how it got there, right? But you need to dispose of it. You need to get rid of the evidence. Well, what are we going to do? Let's see.
Oh no! Some unforeseen circumstances have resulted in you having a human being shaped object at your doorstep. Well, look no further. But we need to be efficient with this, because let's just say this may not be the only time that we run into this, so we don't want to use more chemicals than we have to. So let's measure our human being shaped object to know just how much substance we need to use in order to get rid of the evidence, okay? But how would you do it? My human being shaped object is not a square. It's not a cylinder. It's not even a pyramid. So what am I going to do? Well, let's start by filling up a bathtub. And let's take our person-shaped object. Think of your worst enemy, right? Like so. Give him a nice little frowny face, and kerplunk! Toss him in. What this is this is utilizing what is called water displacement. See, you put in a certain amount of liquid before putting the human being shaped object in, and after you completely submerge your human being shaped object, the water level is going to rise. Well, the difference between your first and second water level is the volume of your human being shaped object. Please keep in mind, I've always said human being shaped object. I've never said actual human being, so there are no criminal charges to be filed here. Thank you.
So now that we have direct means or indirect means at our disposal, we can go into solving these problems now. They're always going to provide us with two of the variables, and we can always solve for a third variable. And there is a shortcut for doing this. If you're still uncomfortable with rearranging and manipulating equations, even though the equation is quite simple, density is equal to mass over volume, once again, there is a little shortcut for that, and we'll show you on the board here in a moment. But for the most part, we're really just going to pay attention to units here, making sure that we are utilizing the same units, making sure that we are ending with the units that the problem dictates for us to end to end. So let's look at this. Wood has a density of 5.5 grams per cubic centimeter. Do recall that cubic centimeter is the same thing as milliliter. What must the volume be of 33.3 grams of wood? So they don't, tell you to end in a certain unit or anything like that. But the way that you plug it in, the way that it's going to come out, it's going to be in cubic centimeters or milliliters, right? But there is the potential that the question could say, put your answer in liters, something like that, in which you would just utilize dimensional analysis to convert milliliters to liters. So now the last thing to consider here is the sig figs. Each of these are measured values here, right? Measured values, which means they contribute to the significant figures of our problem. But because this is all multiplication and division, the least amount of sig figs used in the problem is how many sig figs will be in my answer. So actually, after we move past, actually assessing what the significant figure rules are, it becomes quite simple in these problems. Whatever you start with is how many you're going to end with. And that's pretty much the bottom line for the entire course of chemistry. So density has 2 sig figs, and the mass has 3 sig figs here. Therefore, we're going to end with 2 sig figs in our final answer. And let's solve it on the board, and we'll do example 2 as well.
Before we solve our density problems, let's take a look at what I call a shortcut here. If you already know the density formula, which of course is D is equal to M over V, take a look at this triangle here. Okay, it's a way of knowing how to manipulate the equation to solve for whatever variable you're looking for. As with all of these problems, we are going to give you 2 of the variables. You are simply going to solve for the third. So, for example, if I want to solve for density, what does it look like mass and volume are doing? Well, mass is on top of volume, so it looks like if I do mass divided by volume, I get density. Brilliant. Well, let's say that we're looking for mass. Well, what does it look like density and volume are doing? They're right next to each other. So if I do density times volume, I get the mass. And what if I'm looking for volume? Well, mass is over density. Therefore, if I do mass divided by density, I'm going to get my volume. A couple things to note here, and this also applies to dimensional analysis as well. Oftentimes, they'll use centimeters cubed and milliliters interchangeably. It's very important to know that 1 milliliter is equal to 1 centimeters cubed. So very, very, very important. Let's take a look at example 1 and how I would recommend setting this up. What I would do is I would write down all of the variables that they are giving me, or all of the information that they are giving me. Because if I have this and I have the equation in my arsenal, the really only way I'm messing this up is if I manipulate it incorrectly or I write down the wrong value for the wrong variable. So we see in example 1, wood has a density of 5.5 grams per cubic centimeter. What must the volume be of 33.3 grams of wood? So very obviously, we're looking for volume here. If you don't read carefully, you might plug in one of those values for volume. Density is literally a mass over a volume, so it's very easy to pick out which of the numbers they're providing in the problem, which one of them is the density, because it's got a mass and a volume in its unit. Okay? And notice what's very cool about density is that it is what is known as an intensive property. It is a property about a substance that never changes, no matter how much of that substance that you have. So when it says wood has a density of 5.5 grams per cubic centimeter, it doesn't say what kind of wood this is, but that's a definitive statement. It doesn't matter if I've got a log or an entire freaking tree of it, the density is going to be the same. And it's very, very, very important and critical to know that about density. But we'll learn more about intensive properties next unit. What must the volume be of 33.3 grams of wood? All right. So we're looking for volume, so what I'm going to do is I'm going to cover up the V. What does it look like the mass and density are doing? If I do mass over density, I will get my answer. So we're going to get 33.3 over 5.5. And just like we were telling you and encouraging you to take note of is how many sig figs should I have in my answer? Well, these are all multiplication or division operations. Therefore, I'm going to round to the least amount of sig figs, which is 2. in this case. 33.3 divided by 5.5. Unrounded, I get an answer of 6.0545, so on repeating. So we're going to round this to 2 sig figs, which is going to bring us to 6.1. And because we didn't change the units here, your volume is going to be the same unit that you started out with, which is centimeters cubed, or feel free to put milliliters. They are the exact same thing. Like so. Let's look at example 2. All we have to do is erase the numbers from the previous problem. Granite has a density of 4.67 grams per cubic centimeter. What is the mass of 46.8 cubic centimeters of granite? Pay attention to those units. It's telling you which variable it applies to. Density is 4.67. And the volume is 46.8. So we are very obviously looking for the mass. I've got 3 sig figs here, I've got 3 sig figs here. I just got to make sure that my answer gets rounded to 3 sig figs. If I cover up the mass, how am I going to solve for it? Density times volume is going to do the trick here. So 4.67 times 46.8 equals, unrounded, we get 218.556. We're going to round that to 3 sig figs, as we said before. So my answer should be 219 grams.
So let's look at our last couple of example problems for Unit 1. We're moving super quickly. Example 3, what is the density of a piece of iron that has a mass of 59.8 grams and the volume of 2.8 cubic centimeters? Exact same process that we're going to utilize as the first couple of examples. Just pay attention to sig figs. Both of your measurements here have 3 sig figs. Therefore, there's nothing to worry about, nothing to get mixed up. Your answer is going to have 3 sig figs as well. Example 4, you have an abnormally shaped object that you place into 1.0 liters of water after the volume is shown to be 1.3 liters. So what did they just use there? They just use that indirect method of determining the volume of an object that's not really, traditionally shaped. Perhaps it is human shaped. Either way, we are going to utilize what is called water displacement, and that's exactly what this first sentence is telling you. So neither of these are the volume of your object. However, if you take the difference between them, that is your volume of the object. And 1.3 minus 1.0 is, of course, just 0.3 liters, which only has 1 sig fig. Only has 1 sig fig here. And then the mass is 632 grams. Well, if I've got the mass and the volume, I can very readily solve for the density, but I am going to round to 1 sig fig.
Example 3 reads, what is the density of a piece of iron that has a mass of 59.8 grams and a volume of 2.08 cubic centimeters? This is the easiest type of problem because the equation that we know density to be is already solving for density. So all I got to do is get my mass and divide by my volume, but there's no rearranging to be done here. So we've got a mass of 59.8 grams and a volume of 2.08 cubic centimeters. And our density is simply equal to those values divided by one another. Like so. They both have 3 sig figs, so we're going to round our answer to 3 sig figs. And so our density is equal to 28.8. And this is grams per cubic centimeter. Pay attention to those units with density. Remember, it is mass over volume, therefore your units will indicate as such as well. And for our very last example, example 4, you have an abnormally shaped object. Perhaps it is shaped like a human body. I don't know. That you place in 1.0 liters of water or whatever chemical you're using to dissolve all of your evidence after the volume is shown to be 1.3 liters. The mass is 632 grams. What is the density of the object? All of that information that they are giving you up front is a roundabout way of giving you the volume. This object is not a perfect sphere. It's not a perfect cube. You've learned those equations in geometry, but this thing is not a perfect shape of anything. And so we had to find the volume indirectly, which means we dunked it in water and we utilized water displacement. We took account of what the water was at first and we took account of what the water was after. And the difference in the volumes there is the volume of the substance. So we've got an overall volume. Let's say volume 1, volume 2. Let's be super annoying about this. To find the volume of my object, it's simply the difference of these two volumes, which obviously is 0.3. Now keep in mind, this is just like one of those multi-step sig fig operations that we implemented a little bit earlier on in the video. Because we ended with 1 sig fig here, we are going to round to 1 sig fig at the end of the problem as well. The mass is 632 grams. What is the density? So we're going to solve for density, which the equation's already set up for us. 632 divided by 0.3. And pay attention to your units here. The number's going to get really big because our volume is in liters right now. So we got 2107. Let's just go say that. Like so. 2107 grams per liter. However, that's not correct sig figs. If we're going to round this number to 1 sig fig, this is where it's going to feel really weird. Our answer is actually 2,000 grams per liter. And that's where sig figs can feel really weird because it feels like we are throwing off the accuracy of our measurement completely. We decrease the density by 107 grams per liter here. That seems massive. But the moral of the story today, we are only as accurate as our least accurate measurement. Thank you for attending episode 1 of Corona Chemistry. I hope you enjoyed yourself. Now, go relax. Go watch a show. Okay? Enjoy yourselves. Stay healthy. Wear a mask.
Thank you for attending our, what should we call this? A seminar on the introduction to chemistry. There's many more great pieces of information coming your way. So stay tuned and get ready for the ride of your life. I'm excited. Are you? Happy quarantining, everyone. Stay safe. Wear a mask. Stay fit. Wear deodorant.